In this video, we're going to implement a simple UNet in JAX to learn a solver to the 1D Poisson problem. For this, we will first go over the theory of UNets, then we will describe the concrete scenario that we're interested in, which we will also use as a data generator. It will be a mapping between a force field and a displacement field of a thin string or thin membrane. After this, we are going to implement the UNet in the Equinox deep learning framework, and then we're going to train it with a very simple supervised training loop. Afterwards, we will inspect the training process, produce qualitative comparisons on a test data set, and ultimately also produce a test metric. Let's get started. The channel sponsor Pasteur Labs is currently hiring SciML and software engineering positions. Check out pasteurlabs.ai/careers for more details. Hi and welcome to this new video in the series on neural operator learning. This time we will implement a UNet in JAX. This is a hierarchical convolutional architecture, and we will use it to solve the 1D Poisson problem. This partial differential equation, it's very typical for the class of elliptic PDEs, and it has a lot of interpretations. You can find it in various fields of science and engineering. Here we will use the interpretation that it maps between the forcing field on a one-dimensional string and its displacement, and that we say the second derivative of the displacement is minus the forcing field. Additionally, we will have to provide boundary conditions, and this can be interpreted as if we clamp the string on both ends. You can also to some extent think of it as the string in an instrument, only with the fact that we are not necessarily interested in the temporal behavior, but just its deformation or displacement if we apply a specific force to it. We can solve this PDE with a variety of different methods, but essentially once we solve it, we have a mapping between a forcing function and the displacement. And the UNet that we're going to train here shall be this particular mapping. And in that sense, it also fits in this neural operator framework as a mapping from the forcing function, or from a discretized version of the forcing function, to a discretized version of the displacement. Let's look at the UNet, and for this I have here the original schematic by the paper of Ronneberger et al. From the year 2015. Just note here that our concrete implementation deviates a bit from this. I will talk more about that later. I believe one of the big deviations, of course, is that we look at 1D problems instead of 2D problems. So they always consider images, which are of course 2D, and here we only have a 1D problem, and as such our degrees of freedom can be represented in a vector, whereas in their case they of course need a matrix. So the key idea of UNet, I think it's very beautiful, because if you are familiar with scientific computing and learned about how to solve elliptic PDEs, you might have heard of an algorithm or methods or a class of methods called multicrit. And those are one of the most efficient approaches you can do to solve the elliptic or Poisson problems here. And their core idea is that the Poisson equation can be solved on a hierarchy of different crits, from a very fine resolution to a coarse resolution. If you use a specific subset of methods within these different resolutions, you can kind of reduce the error in the solution to the PDE very quickly and find solutions to the PDE also very efficiently. But the core idea is that we start at very high resolutions, let's say 1,000 degrees of freedom, and then have a hierarchy of crits all the way down to only a handful of resolution points. And this idea is also somehow found again in the UNet architecture. And I'm pretty sure they also somehow was a motivation for this original UNet architecture. But how does it work? So you see a variety of different tensors in here, and they come in this U format. I mean, that's also how the name UNet probably came to mind. So what happens? So in the left we have our input. Again, they use images, and here they have an image with only one channel, and then the output. So they use this UNet for segmentation. So the output is another image, and this output image has two channels. Here in our particular case, the output only has one channel, because we have this mapping from a forcing, which is only one channel, to a displacement, which is also only one channel. Okay, what happens then? So they have an lifting. So lifting means an kind of a mapping into a hidden or latent feature space and they map from this one input to 64. We will use a little less because that's already quite a huge architecture that they have here. Then the core idea is that in this U path going downward, they trade spatial resolution for feature resolution. And in that sense, that means we have here an around 560 by 560 dimensional image. And then if we go down one layer, it is only half of the spatial size, but has twice the feature count. And then they repeat this process 4 times, and in the lowest level they only have a resolution of 30 squared and 1024 channels. On the right half of the right arch of this unit, we kind of transpose that way in that we trade back spatial resolution by giving away channels. And on top, we also have skip connections to bring over the information from the left arc. And as such, we then ultimately go to the desired output shape that we want. Each of the levels basically does 2 operations. So we first have in this kind of baby blue arrow a downscaling or down resolution. They implemented a max pooling operation, but we will just use a strided convolution. Then they have the double convolution, so this is a very similar concept as they have here. So these are just 2 sequential convolutions with an activation functions, and then essentially this repeats over and over. This down here is also sometimes referred as the bottleneck layer. So this is the forward convolution in the lowest resolution, and then in the upwards parse they again use this double convolution concept, which they say is like 2 3x3 convolutions and a ReLU activation. And in the purple or light purple color, they have an up convolution. So it's kind of the transpose process of reducing spatial dimension. So here we will increase spatial dimension. And then ultimately, as the very last layer, they have a projection. This is just a linear 1x1 convolution to reduce or to map between the hidden channels, or to go back from 64 all the way to 2. Let me introduce you to the concrete scenario. So as said, we will solve the Poisson problem. We will use our own data generator here. For this, we will select a discontinuity as a forcing function. So we will say that the force is 1 if our coordinate is between a lower and upper limit and 0 otherwise. And we will randomly draw these limits from uniform distribution. And this allows us to create 1000 forcing functions. And then we will discretize them on a grid of 32 interior nodes. But you will see that in a second. Then the reference solution, so this is basically how we're going to solve the Poisson problem to create a data set, is by a 3-point stencil and a direct linear solver. And then we basically have a data set consisting of 1000 discretized forcing functions and their corresponding 1000 displacement fields, also discretized. Those we will split for 1 into a train test, and then basically we'll just train the UNet with a mean squared error on that particular data set. I want to highlight a couple of modifications from this particular schematic I showed you. I mean, obviously, of course, we are in 1D instead of 2D, but then we have some other important changes. So as already mentioned, for the downscaling part, we will not use the max pool operation, but at strided convolution. Then the other change that I want to do is that the downscaling on the upscaling are now 3x3 convolutions with a stride of 2, and here they basically have 2x2 convolutions. Then I also want to use padding. So basically in the original implementation they don't use padding, and you can also see that here. So the input resolution is 572 by 572, and then by one application of a conv layer it reduces by 2 per axis, and that basically means we have not used any padding, so it's just a valid padding. Here we will use same padding, and this also, I think, simplifies a bit the burden on your head of understanding how this unit works. Most units also come with normalization layers like a group norm or batch norm. We will leave them out for simplicity, and here we will have a variable number of layers you see, or levels. So basically here in the original unit you had 4, but I want to give this as an arbitrary argument, and then later on we will just use 2. So basically the bottleneck layer is already on this particular level. Then let's go down and remove this hello world statement, and we can start with the imports. So we will first need a JAX, then we're going to import jax.numpy as JNP. Then we will also need jax.treeutils, so jax.treeutil, and we will import this as JTU. Let me scroll down a bit. Then we need Equinox. Equinox is the deep learning framework we use. There are a lot of deep learning frameworks in JAX. I particularly like Equinox because it is single batch by design, and I think it's also not very intrusive in comparison to some other deep learning frameworks. If you want to see a good video on where we make usage of this single batch design, then I would recommend you to check out the tutorial on the deep operator network, which definitely benefits from the single batch design in conjunction with the JAX.vmap function transformation. Then we will also need to import typing. So from typing, import callable. This is because the Equinox networks that we're going to implement need to have their attributes typed, and since we somehow need to save an activation function, we need that typing information. Then we will import Optex. Optex is a JAX-based gradient processing library providing us with the Atom optimizer. Then we will import matplotlib.pyplot as PLT for visualization. And I will also import tqdm.autonotebook import tqdm. And tqdm is just a simple progress meter. And then as a small bonus here, I want to set the plotting style to use the dark background just to have this a bit more nicely here, and then execute that. I think this was a typing mistake, and here we go. I will now copy in the data generation code. So let's quickly go over that. If you want to have more details, I would recommend that you check out the video on the physics-informed neural network I also did, where we do something very similar, also implement a simple solution to the Poisson problem, and I will discuss it in more details. So essentially, let's go over these constants. So first we say we discretize our domain into 32 degrees of freedom. Since we have Dirichlet boundary conditions, that only includes the interior nodes. That's also visible here. If we generate the grid using linspace, we essentially add 2 points, but then only extract the interior. Here I say that the number of samples are 1000 and the domain on which the problem resides, so essentially this is the L of the introduction, is going to be 5. So 5 units. Then we will set up the tridiagonal matrix representing the discrete Poisson problem, or using a 3-point stencil. We have a solver function that essentially invokes the direct solver from JAX NumPy. Then we have a function that creates a discrete continuity by drawing the lower and the upper limit from the uniform distributions, as mentioned earlier. And then essentially we will make usage of JAX-vmap in that we first create as many random keys as we have samples, and then we will vmap this continuity creator on the keys, and then ultimately we get the force fields out of it, and we can vmap the solver on the force fields to get a displacement field. If you were to inspect the shape of these two arrays, those would be 1000 by 32, because we have 1000 samples, and each, the force field and the displacement field, is discretized on 32 degrees of freedom. Now that we are working with convolutional architectures, we need to obey the convention that those layers have, and typically this is batch, channel, spatial. Kind of that we have here just force fields with batch and spatial means we have a singleton channel axis, which we can also insert here. So this basically means now we have as many number of samples, then we have 1, and then we have a number of spatial dimensions. Let's execute that. It actually runs fairly quickly. Then we can inspect the shape. So let's just first do the force fields dot shape and then the displacement fields dot shape, and there we see they are 1000 by 1 by 32. Let's discuss what those two actually mean. So because so far this has been a quite abstract thing, for this let's plot them. So let's use plt.plot on grid, so that we use here from that cell, together with first the force field, and say force fields 0, 0, to index the 0th force entry, and then a 0 to remove the singleton axis, and attach the label of force field. And then let's do the similar thing for the displacement field. So grid displacement fields 0, 0, and attach the label of displacement field and activate the legend. Let's run that. And here we go. So basically we have our field or our domain going from 0 to 5. You also see that all the two lines don't include the value at 0 and 5, and that's because at those 2 points we have the Dirichlet boundary conditions, which were 0. So it turns out that both the force and the displacement has to be 0 at these boundary points. They are not plotted because they're not part of the degrees of freedom array. You could, but for here we can also think that virtually both these lines will have 0 value here. And then we have a force field, so it kind of looks like there's a kind of an ascent here, but you have to think of it as a discontinuity. Just because we don't have enough resolution, it kind of looks like we have that ramp here. But think of it now as following, that we have this string clamped on both ends, and then you kind of put your fist maybe at particular from this particular point to that particular point, and then just push upwards. So on a subset or a subinterval of the string, you apply a constant force, and this force also does not vary. And then in orange, or in, I think it's more of a yellow, you actually see the displacement, and of course because you push upwards, the string displaces upwards, and it kind of does so in this arc shape. So now basically our data set consists of a couple of these relations. So we have 1,000 of those mappings from the blue to the yellow. Let's also inspect those. So let's plot a couple of the force fields first. So let's do plt.plot on grid and then force fields, and let us extract the first 10, then 0 again to reduce or to index the singleton channel, and then I have to do a dot transpose for the correct batch plotting and a semicolon to suppress the output. And now basically you see, so unfortunately it only shows the first 4 or something, but essentially what you see here, we have a couple of force fields. All of them, they have the same upper limit, or like are both at 1 when they are in their upper range here, but the point where the discontinuity starts on the left and on the right varies. Let's also plot the corresponding displacement fields. So plt.plot on the grid and the displacement fields, the first 10, 0, and then transpose. Let's see that. Okay, now you can also distinguish them more nicely. All of them have this arc shape, but some of them have a higher or lower peak, and you also see that kind of their shape is also a bit different. And this is caused by how the force acts on that. And essentially now the task of the UNet is to use the set of forces and displacement to learn the relation between the two. For this I want to do the train test split. So as mentioned in the intro, we will do a 4-to-1 train test split. So for this, let's first compute the split index and say that this is number of samples, integer divided by 5 multiplied by 4. And then we will get train x and test x by slicing out from the force fields, because the supervised mapping is of course from force field to displacement field. If it was the other way around, it was just a matrix multiplication, and here UNet actually has to learn to solve this system of equations or to solve this PDE. So the force fields, let's index them up to the split index, and then let's index them from the split index upward. And we can do something similar for the train y and the test y by using the displacement fields up to the split index and then the displacement fields from the split index upward. Then let's look at the shape of these new tensors. So train x.shape and train y.shape. They are both 800 by 1 by 32. And then we have test x and test y.shape. Sorry, forgot the shape here. And those are 200 samples. Now that we've created our data set, it's time to implement the architecture. For this, let's go back up and see that there are some repeating blocks. So these two yellow arrows together represent this double convolution I mentioned earlier. And to structure the architecture a bit more nicely, I want to create a separate block for this. So let's start the implementation of the UNet with that block and call it the double convolution. So let's say class double convolution, and it shall subclass from Equinox module. Again, Equinox is our deep learning framework, and it requires us to first write out all the attributes. And this double convolution obviously consists of convolution 1, which is equinox.neuralnetwork.convolution. And then we have convolution 2 is another equinox.neuralnetwork.convolution. And it also has an activation function. And for this we need the type callable. And that's also why I needed to import that from typing earlier. Then let's define the constructor. So first take self. Then we need to define the number of spatial dimensions. So as mentioned here, I want to have a one-dimensional UNet, but I want to still have this as a free parameter. I think that's very nicely to define your convolutional architecture independent of the spatial dimension, but of course you could also hard code that. Then we need to define the number of in-channels. So in-channels, it's another integer. Then we need to define the number of out-channels, which is also an integer. And we need to find the activation, which is a callable. And then we will use as a keyword-based argument. So that's a very typical pattern you see in these Equinox architectures, that we hand over the JAX pseudo-random number key as a keyword-based argument. And that's of course needed because all pseudo-randomness in JAX is easily reproducible and has to be provided by explicit state. Okay, first step in the constructor is to split our key into a convolution 1 key and a convolution 2 key with jax.random.split, and then apply this to the key and say we want to split it, sorry, no, not free, but we want to split it into 2 keys. And then self.conf1 is equinox.neuralnetwork.conf. So this is also the reason I used the number of spatial dimensions as a first argument here, because then we can easily hand that over to the general conf routine, which also is independent of the number of spatial dimensions. So let's do number of spatial dims. Then it provides us with the option to select the in-channels, and the in-channels are of course also the in-channels to the double conf. And then the out-channels are the out-channels. The kernel size we set to 3 because we want to have a 3x3 convolution. I mean, 3x3 is in an image context. Here, of course, we are in 1 dimension, so it's only a free convolution, you might say. And in order to get a same padding, we need to set padding to 1, such that this convolution does not alter the spatial size of the tensors it operates on. Also, we need to provide the key, and this key will be the C1 key. Self.convolution2 is very similar. So again, equinox.neuralnetwork.conf. Let me scroll down a bit. First providing the number of spatial dimensions. But for the second convolution, the number of in-channels is actually out-channels, because the first convolution, or in other words, if there is a difference in the number of in-channels and out-channels, the first convolution already did the channel adjustment. So this one does no longer change the number of channels. So it's just a mapping between out-channels and out-channels. It has the same kernel size, which is 3, and the padding is 1. The key shall be the C2 key. And then let's also save the activation function in its corresponding attribute. Then we can implement the forward pass via the call method. So __ call, and this one shall take self as well as x, and x is a jax.array, and in that case it is of a correct format. So in the 1D case it has to contain channels and spatial. And this is very important because the networks defined by Equinox are single batch by default. So if we are in 1D, it only has 2 axes. We will also see that in a second how that affects the UNet. And then I believe the forward pass for this double convolution is very straightforward. So let's first apply the first convolution, then we will apply the activation, then we will apply the second convolution, and ultimately we will apply another activation, so self.activation on x, and then we can return x. Shift enter registers that double convolution. Then let's continue with the actual UNet. So let's say class UNet is again subclassing from equinox.module. And then we need to define its attributes. So here I will do the following, in that we separately save, so let me go back up here, we will separately save the lifting, so the first double convolution, and we will separately save the projection, which is that reddish convolution we have at the end. And then we will create a list of downscaling and double convolutions for the left arc, and a list of double convolutions and upscaling for the right arc. And in that sense, this is a bit different from some other implementations you see, that the bottleneck layer is not separately an attribute, but it's part of the double convolution of the left arc. And think of it as following, so that here we have 4 levels going down, we have 4 double convolutions in the left arc. So here's one, there's one, there's one, and there's one, make it 4. And then we have 4 downscalings, so by the downscaling or changing the resolution in the Babel blue, which is 1, 2, 3, 4, and on the right arc we have 1, 2, 3, 4 upscaling, and then we have, or upsampling better, and then we have here in the yellow we have 1, 2, 3, 4 double convolution. So in that sense we can use lists of identical length, which is 4, and in that sense also means that the convolutions in the double convolutions in the left arc start at level 1 and end at level 4, and the convolutions in the right arc, so if we think about it going from up to down, start at level 0 and end at level 3. So they are 4 in count, but they operate at different resolutions. And I think this can be a bit of a headache when implementing that. So let's just keep that in mind, and I will go back up when we actually are at that point. But let's go first back down, and this was just to motivate why I'm using the particular attributes that we have here. So first we have a lifting, which shall be a general Equinox module. Then we have a downsampling blocks, and these downsampling blocks are a list of Equinox modules. So ultimately those will be the strided convolutions. And then we have the left arc blocks, and the left arc blocks will be a list of equinox.module. And I believe probably we can make it even more verbose in that we say that the lifting is going to be a double convolution and the left arc blocks is going to be a list of double convolution, whereas the downsampling block will be equinox.neuralnetwork.conv for the strided convolution. Then we have the right arc blocks, here we go, which is another list of double convolutions. And then we also have the upsampling blocks, which will be a list of equinox.convolutions. And those will be strided transpose convolution, you will see in a second. Then we have the projection, which is this final linear 1x1 convolution for adjusting the channels. This time I want to go the other way in creating the constructor after we created the call signature, because I believe the call signature gives us more intuition how to actually do the constructor. So let's do define call first on self and x is again a JAX array of the required shape. And then what happens? I mean, the first step is very simple. We just first do the lifting on x, and then I want to implement a list to capture the skips. So x is going to be our operating variable that we will follow through the U path, but we somehow also need to save the skips, and this is what I want to do in a list. So whenever we are at a point where we are on a skip connection or where we need the entry later on, we will save them in a list. Let's go down and say that this is this x skips, and let's have that as an empty list for now. And then we first consider the left arc. So let's call this the left part of the arc. And I see I also called this arch, not arc. So let's remove the H and say left arc blocks. Okay, this shall be a loop between the downsampling and the left arc blocks. So let's say for down and left in zip of self dot downsampling blocks and self dot left arc blocks. Basically do the following. First, save the skip connection. So xskips dot append x. So basically think about it like this. So let's say for instance we only had one level, so let's ignore all the lower part here, and this essentially will already be the bottleneck layer. But then what happens, so we first save that point to have it as the gray arrow later on, and then we will do blue, and then we will do yellow. So first downsampling and then the double convolution. So x is self dot down applied to x, and then x is self dot left applied to x. Oh, sorry, should not be self. That's of course not using that variables correctly. So first down and then the left arc. And then ultimately, once we go all the way through the left arc, we have to go back up. So we do for right and up in zip of reversed self dot right arc blocks and reversed self dot upsampling blocks. And then now we have to be careful what goes on in these particular orders. So let's now imagine we are here, we are at the bottom right, we fully went through the left arc of the UNet, and then what happens, so we do the baby purple stuff to go up in spatial resolution and trade channels for that. Then we concatenate, so we take the skip and concatenate and then do another double convolution. So the order is upsampling, concatenation, right convolution or double convolution. So let's do exactly that. So first we will say x is up on x, then concatenation, x is JNP dot concatenate on x together with x skips dot pop. So pop is basically taking the last entry out of the list and also removing it, that it's no longer part of the list. And it also makes sense because you can also think of it as a stack. So we are stacking on top of this x skips, and then we are taking from the stack in order to do our concatenation. And that also makes sense because the stack will have at the top the last or the lowest skip connection, and then by a pop it will be removed. So it's essentially also the tensor that we want to have here. Okay, then we do the concatenation, and for this we have to provide the axis over which we concatenate, and this is axis 0. And this is probably different from an implementation of a UNet in a different framework, because Equinox is single batch. That means that there's no batch axis, no leading batch axis. The channel axis is actually at the very front. If you were in PyTorch, that would probably be 1. Or if you were in Flex, for instance, then I think it would be a different one, but at least it's also not 0. And so let me leave the remark here that Equinox is without batch axis by default, and hence channels are at axis 0. Of course, later on we will then use the vmap command to make our network operate on more than just one sample, but this vmap command cleverly rewrites the call signature for us to still do the correct concatenation. So we did the first step, upsampling, then we did concatenation. Last one is to do the double convolution, so x is right on x, and then we are back up. So essentially after going through both loops, and let me add the comment here. So this is the right part of the arc, or the right arc of the UNet, however you might want to call it. After these both loops, we are now at that particular tensor. And the final thing we have to do is our projection. So going from the hidden channels all the way to the output channels we desire with our 1x1 convolution. So let's do the projection and say that x is self.projection applied to x, and then we can return x. Let's now use our intuition on the call method to implement the constructor. So let's go a bit up and then define the init method with self, and then we again first take the number of spatial dimensions, which shall be an integer. Then we have to define the in channels, an integer. We have to define the out channels, an integer. We will have to define the hidden channels. So this is basically referring to the first hidden channels that we have, so in the upper level. In their case it was 64, and of course then we have increasing number of hidden channels, but this is kind of implicitly computed, so that we then go from 64 to 128. So let's go down. Hidden channels being an integer, we will set the number of levels. So number of levels mean how often do we go down. So in the original UNet we have 4 levels. Here we will only do 2 since that's sufficient for our problem, but I want to have the constructor being flexible on the number of level. Then we have activation, which is another callable, and then ultimately similarly we need the key, which is the pseudo-random number key for reproducibility. So then let's start with the constructor. First step is to define the lifting and the projection layer, because they don't need a loop to be instantiated. So let's first split a key into 3 keys by saying key, lifting key, and projection key being jax.random.split, and then the key into 3 parts. And then we can instantiate first the lifting, so self.lifting, and we said that one shall be a double convolution. So we will use our newly created class doubleconv and instantiate it with the number of spatial dims, the in channels, and the hidden channels. Finally, it needs an activation. So we will hand over the activation function, and we will set the key to the key. Oh, sorry, this is wrong. We set it to the lifting key, of course. Then we have the projection. The projection was a convolution, and not just any convolution, is a 1-by-1 convolution, or 1-by-1 again is a notation for 2D convolutions, but it will only have a kernel size of 1, meaning that it does not need any padding, and also it just adjusts the channels. So we do equinox.neural-network.conf, provide the number of spatial dimensions. The in channels are the hidden channels now, and the out channels are the out channels. The kernel size shall be 1, and the key is the projection key. So here we go. And then we have defined the projection layer. Then in order to instantiate the list of other components, I first want to create a list of channels. Call this the channel list, and this one we will use a list comprehension and say that this is hidden channels times 2 raised to the I for I in range of 0 to num levels plus 1. So what happens here? So this is a range starting from 0 all the way to num levels plus 1. So in Python, always ranges are excluding the upper limit. So we do a plus 1. And this essentially also gives us a list of num levels plus 1 entries. So hypothetically, let's set num levels to 4 as it is in the original UNet architecture. But if we have 4 levels, this means we go 4 levels down. So 1, 2, 3, 4. But in total, there are 5 levels. There is this unchanged resolution level, then the level where the resolution was changed once, twice, 3 times, and 4 times. And this is represented within this list. So this list says here it's 64, here it's 128, 256, 512, 1024. And this will be the hidden channels list, or just channels list. Then let's first have the empty lists on all the 4 stuff that we need to fill up. So we have first the downsampling blocks with an empty list. Then we have the left arc blocks with an empty list. We have the right arc blocks with an empty list. And we have the upsampling blocks with an empty list. And then we can use the channel list to iterate between the level transitions. Because essentially what we need is, we need to know the information of the upper levels channel and the lower levels channel. And then we kind of have that purple is operating on the upper levels. The left arc double convolutions is operating on upper levels to lower levels. Then the right arc, so this will be the corresponding one here, will be operating on lower levels to upper levels. And then the up convolution will be from lower levels to upper levels. So let's implement it as that. So let's go to here and then create a loop and say for, in brackets, upper level channels and lower level channels in zip. And let's move to the next line and say channel lists indexed all the way, but excluding the last element, and channel lists starting from the first element all the way to the end. And then we first split our key again into a key, a down key, a left key, a right key, and an up key by doing jax.random.split the key into 5 components. Then let's first instantiate the downsampling block. So self.downsampling block.append. And here, how did downsampling work? So in the original UNet, it was a max pool operation, but for this implementation, I want to use just a strided linear convolution. So we do equinox.neural-network.convolution and then num spatial dims. What is the in channels? So the in channels is the upper level channels and the out channels is the upper level channels. So the downsampling does not alter the number of channels, but it alters the spatial resolution. And to do so, we will first set the kernel size to 3. So I mean, this does not greatly change the spatial resolution, but importantly is stride being 2. So it is a strided convolution. And then I also set the padding to 1 because the padding of 1 kind of compensates the kernel size of 3. So if stride was 1, that would not change the spatial resolution. But now if we set padding to 1 and kernel size to 3, stride of 2 exactly halves the resolution. And then we have to provide a key, and the key will be the down key. So this is the downsampling block. Next up, let's implement the left arc block. So left arc blocks.append. And for this one, we need a double convolution. So let's do double conv on the number of spatial dimensions. And now the double convolution on the left arc was actually changing the channel or feature channel count. So it does so from upper level channels to lower level channels. Because as we know from our call signature, the result of having one step done in the left arc is having the resolution halved and the channels doubled. And this is what happens here. So first resolution halved, channels doubled. Let's set the activation because this one is an activated block and the key shall be the left key. So the downsampling is just a linear convolution. There is no activation here, but the double conv is activated. Then let's go to the right half of the UNet. So first we will do the right arc blocks and then append to it another double convolution with the number of spatial dimensions being set. But now what is the in channels? So the in channels is the lower levels channel and the out one is the upper level channels. So take a look what happens in the right part. So we first do an up convolution, we implement it in a second, but I believe probably if it's better to first do it and then discuss the double convolution. So let's finish its instantiation by providing the activation and set the key to the right key. And then let's do the upsampling blocks.append and append an convolution transpose. So conv transpose and say the number of spatial dimensions. And then the in channels for the transpose convolution is the lower level channels and the upper level channels. So let me first finish the conv transpose and then we can discuss that. For this, we will set the kernel size to 3, we will set the stride to 2, and we will set the padding to 1, and then we will set the key to the up key. Okay, let me first discuss. So here the conv transpose does two jobs. It changes the spatial resolution, but it also changes the feature count. Let's take a look at the UNet schematic and look, for instance, here in the bottom right. So with the first baby purple arrow, we see that the lower one has, so you kind of in the width, you see the number of channels, and then the height, you see the spatial dimension. And if we go one level up, it doubles the spatial dimension, but halves the channel count. So this is in contrast to what we have in the downsampling with the baby purple, which does not change the feature channel count, but the spatial resolution. And the reason the up convolution makes that change is because we will then concatenate the skip connection in, and then the concatenated array will again have 1024. So we halve the channels from the lower level to then, after concatenation, have the same number again. So if we go down here into the call signature, we see that we first make the up, then make the concatenation, and then make the write. So up doubles spatial, halves channels, then concatenation means we still have double spatial, but now we have again same number of channels, and then the write halves the channels again. So that also explains why the double convolution takes in the lower level channels despite the conv transpose outputting the upper levels channel. Because if we concatenate two arrays with upper level channels, we actually get the amount of lower level channels. So I mean, it's a bit counterintuitive that lower level channels is higher, but I mean, it makes sense because the lower we are in the UNet, the higher the number of channels are, the less spatial resolution there is. So again, once again, we have the conv transpose mapping from lower level channels to upper level channels, because we then do the concatenation to again have lower level channels, which is the input to the double convolution, which then returns upper level channels, which is in the next iteration of that loop, the lower level channels again. It kind of explains the signature here, or the way we instantiate it. One more point for the conv transpose is, if you look at a doc string, you see it has next to padding an argument called output padding. And that is because whenever we halve resolutions, or whenever we do some strided stuff, there is an ambiguity in between the mapping. Because, for instance, if you take a resolution which is an even number, you can easily halve it from 10 to 5. But if you have an odd number, then its halving will be rounded either to the seal or to the floor. And this output padding is to compensate for that. And in order to make the UNet work, we need to set the output padding, sorry, not the out channels, but the output padding to 1. Okay, long story short, that is our UNet. Let's shift enter to execute that cell. Let's make a first test if the implementation is correct. So let us instantiate first the UNet, and I want to call it the Poisson solver UNet, which is the UNet. And then first we are in 1D, so one spatial dimension. We have one input channel because the forcing field has one channel. We have one output channel because the displacement in 1D is described by one channel. And I want to set the hidden channels to 32 and the number of levels to 2. And the activation function shall be the relu, so jax.nn.relu. And as a key, we can, for instance, use jax.random.prng key and use a 0 here. So let's see if the instantiation works. Takes a bit, but that's fine. Okay, at least one step seems to be good. Then let me copy in function to count the parameters. So this is just using the idea that Equinox modules are pi trees, and we can call it on the UNet, so Poisson solver UNet, and see our network has 188,000 trainable parameter. That's quite a lot. And if you think about it, that we only have 32 hidden channels, but the key concept on why the parameter count is so high is that in each level we double the number of channels, and we have 2 layers or 2 levels. So it means that in the lowest level we have 32 multiplied by 2 to the power of 2, which is 32 times 4, which gives us 128. And the number of parameters in convolutions grow with the number of channels being mapped. And as such, we have a lot of parameters in the lower level of the UNet. Never mind, it's still an acceptable amount of parameters to train here on my laptop CPU. Let's also check if it works. So for this, I want to call it on the train data set. For this, we will use jax.vmap because, as mentioned, Equinox modules are, or Equinox networks are single batch by default, so they don't have a batch access. And if we use vmap, it rewrites our function, so in that case the Poisson solver UNet, to take an additional batch access. And let's feed it with trainx. And that should work if that erases any errors. Okay, so far so good. At least the forward pass works without throwing errors. And that's also a crucial part, because sometimes when you implement units, you will get some shape mismatches when the concatenation or whatever not works. So it's, I think, a good sanity check to see if the operation of the forward pass just works as is. So let me delete that. And then let me restructure a bit. So I will cut from here and paste that in here. And then we can delete that line and count the parameters and say that this is the parameter count and print that out, the parameter count, because I'm creating here a new cell in which I want to do the training loop. But in order to do the training loop, we also need a data loader. So JAX does not have a data loader by default. You can implement them very easily. Let me just import or paste in here a very simple training loader I usually use. So that works on arbitrary pi trees. We don't have to go into too much detail, but generally it just requires a handover of data, which can be a pi tree. In our case, we have a supervised learning problem. So we will hand over a tuple of input and output data. We have to hand over the batch size, and we have to hand over a key, because of course we have random shuffling, and everything that is pseudo-random has to be traceable and kind of reproducible, so we need a key. So with the data loader, let's implement the training loop. So let's say that here, this is the training loop. So for this we have instantiated the network. Then we need to set up the optimizer. As the optimizer, we're going to use the Adam optimizer with a learning rate of 3e-4. And then with the optimizer, we can set up an optimizer state. Because the Adam is a stateful optimizer, it captures momenta. So we will say optimizer.init on equinox.filter on the Poisson solver UNet with the filtering rule equinox.isArray. That sounds a bit strange. If you're not familiar with JAX training loops or Equinox training loops, I would recommend that you check out the video I have linked up here, which is on a more simple Equinox test case where we just train it on learning the sine function, and there you have more details on why we do the things we do. But for now, this just means that we extract all the parameters, because the unit also consists of the activation function, which of course is not trainable, and it just extracts all the trainable arrays. And you can think of it that it creates this 188,000 dimensional parameter space that in which our optimizer moves. Okay, then each deep learning training needs a loss function. This loss function takes the model, which shall be the current state of the unit, as well as x and y, so our supervised training pairs, input and output. Then we will first make a prediction with the model by saying jax.vmap on model, and then this takes an x. Then we can compute the mean squared error as jnp.mean on jnp.square of y prediction minus y. And then this just returns the mean squared error. And then we will pack all the training updates, so in one update step of the parameters in an update function. So let's say define update function, which takes a model, a state, x and y. And then it first produces the loss estimate and the gradient using an automatic differentiation function transformation. So we will say loss and gradient is equinox.filter value and grad on the loss function applied to model x and y. So this returns the loss function executed with these particular inputs, but it also returns the derivative of the loss with respect to the model, and this is what we need, so the derivative information on all the parameter entries. Then we can say updates and new state is optimizer.update on creds state and model. And then these updates, or sorry, it's not creds, it's just cred. And then these updates are going to be fed into our network by creating a new state of the UNet and say that we have a new model being equinox.apply updates on the model with the updates. Sorry, model and updates. And then this update function shall return the new model, the new state, and the loss. And since the update function is the greatest computational burden within the training loop, we will JIT compile it. So we will say add JAX.JIT in general, but since we're working with Equinox modules, we need Equinox's filtered routines. So we will say add Equinox.filter JIT, and there we go. So we have an update function. Let's create an empty list and call it loss history to record the training loss over the training. And then, of course, since the dataset shuffling requires a pseudo-random key, we will create a shuffle key and say that this is jax.random.prng key, and let's provide a seed. Let's, for instance, use 151. And then we have two nested loops. The outer loop will be the number of epochs we do, and the inner loop is over the batches or the mini batches. So we will say for epoch in TQDM on range of 100 to perform 100 epochs. And then in each epoch, we need to split the key into a shuffle key, and let's call it a sub key with jax.random.split on the shuffle key. And then we can use the data loader. So the data loader is a generator, so it uses this yield statement. So we can just use it to create a loop to say for batch in data loader on a tuple with train X and train Y with a batch size of 32. So this is just something I fixed here, and the key being the sub key. And then we have our call to the update function. So we say Poisson solver UNet together with the opt state, and the loss is the update, not update display, but update function applied to Poisson solver UNet opt state. And then we will use star batch, because batch is going to be a tuple of the subset on the train X and the train Y for this particular iteration within the epoch. And since the function signature requires us to hand over those two as positional arguments, we will just unpack the tuple with a star in front. Ultimately, let's append the loss to the loss history, and then we can fire off the training. So first we have a print of the parameter count, same as before. Then we have some initial compilation time, and then the actual execution of the training commences. So here we go. After around 1 minute and 30 seconds, the training finished. Likely if you execute that on a modern GPU, that will be way faster. Let's inspect the loss history by doing plt.semilog.y on the loss history list. And there we go. So here on the x-axis, we see the update iteration. So we have 100 epochs, but still we see 2,500. That's because in each epoch, we of course have multiple update steps with a batch size of 32. And if you remember, we had 800 samples within the training data set. So roughly, let's say 20 to 25 mini batches per epoch. And if you multiply that with the 100 epochs we do, you see that we are roughly between 2000 and 2500, more towards the 2500. Okay, then we see we have the typical two-phase dynamics. So we have the transient phase of deep learning, where we reduce the loss by quite substantial orders of magnitude. Initially, we are at, let's say, 2 times 10 to the 0, so a 2 loss. And then we go down to, let's say, 10 to the minus 3, 10 to the minus 4. And then we enter a regime where it looks a little bit more oscillatory than before. Of course, these little oscillations in here are the mini batches, but then towards the end, that's usually an indication that we are reaching a state where we are almost converged with the network. So I think that's a reasonable duration of the training. Of course, certain modifications like a learning rate decay can be useful in order to suppress these oscillations towards the end, especially the cosine decay. I think it's a nice schedule because then the model very slowly fades out. Let's see if the network at the final state, so at the end of the training, is any good. So let's plot it together with the corresponding ground truth solution. So for this, let's first create a constant. Let's call it batch I, because I want to vary and see how it works on different inputs, and set this to 1 for now. And then we will first plot the force field, so crit. And of course, now we will be using the test data set. So we will do test x and then index it at batch I, and 0. We again need the 0 in order to remove the singleton access. Let's attach the label of force field. Then we will do plt.plot on the grid together with the test y and indexed at batch I and 0, and attach the label of, let's call it GT for ground truth, and say GT displacement field. And then finally let's add the prediction of the network. So we do grid and then the Poisson solver UNet applied to test x and indexed at batch, so that it only works on one input. And then we also need to remove the singleton batch access. And then let's say label is prediction and activate the legends that we see our labels. Executing that, here we go. So we again have our force field, and then we have the ground truth displacement field. It's barely visible, and the prediction purple. Let me maybe open that in a separate window. And if we zoom in, I mean, unfortunately it's very low resolution, but you see that the yellow curve is only barely visible behind the purple curve. And that's a good indicator that our network somehow learned something meaningful. So it matches the yellow curve very nicely. Here's a little bit of a mismatch here also as well, but that's, I think, good enough. Let's check on a different one. Let's go to 0 maybe and see there it also is fine. As you notice, those there's of course not that big of a variation between the shapes, since we always have this discontinuous force field, but I think that's still a challenging training scenario for the UNet, but that's cool. So let's go to 5 maybe as well. Yeah, here is a bit stronger mismatch, at least something where the UNet did not work that nicely, but of course that's also barely noticeable. Very nice. Okay, cool. Let's also assess the performance of the UNet quantitatively. And for this, I want to do this in terms of the mean normalized L2 error. And for this, I want to create a function which we will then vmap over all the prediction and ultimately aggregate a mean and standard deviation. So let's call this first the normalized L2 norm. And this will take a prediction and a reference. And those are now just single batches, so one batch. And we will first compute the difference norm by jnp.linalg.norm of prediction minus reference, and then we will do the reference norm, which is just jnp.linalg.norm on the reference, and then the return is difference norm divided by reference norm. So executing this is now a function that works on a single batch. Before we can call it on the network predictions, we first have to get the network predictions. So let's say test predictions. And now this is the difference, that instead of having just one prediction, we will do it on the entire test data set. So let's say JAX.vmap on the Poisson solver UNet applied to test X. This gives us the test predictions, and then we can get the test errors by saying JAX.vmap of the normalized L2 norm applied to the test predictions and the test Y. This gives us the test errors. So if we inspect the test errors shape, they are 200. So we have a test error for each entry in the test data set, and then we can aggregate that. So for instance, with a mean, and say mean of the test error together with its standard deviation on the test error. And then we see that the mean test error is 0.006. So it's 6 times 10 to the minus 3. It is in the third digit after the comma. That's relatively low. There is a bit of a standard deviation, not too high though. I think that's a fairly good fit. And we also saw that qualitatively, of course, there are potential improvements. We could make the UNet have more parameters, more levels and so on. Or we could also increase the difficulty of the scenario by having additional forcing function shapes, or maybe even go to 2D. But I think for this very simple introductory case, that is more than sufficient. This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There's more content on neural operators, on architectures in JAX and Equinox, and I'm pretty sure you will find something interesting here on the channel. Here you will now see similar videos, and I hope to see you in one of the future videos.